In a previous video on the consumer's utility maximization problem, maximize utility subject to a budget constraint, we used graphical arguments to show that interior solutions are characterized by two equations: the marginal rate of substitution, the slope of the indifference curve, equals the marginal rate of transformation, the slope of the budget line, and that the consumer spends all of their money. When solving this type of problem, a standard technique is to take the ingredients of the problem to form what's called a Lagrangian, which includes this new variable lambda, pop the utility function here, rewrite the budget constraint like this, pop that here, then find the values of each variable so that these partial derivatives are simultaneously equal to 0. It's useful to have a good idea of where this approach comes from and why it works. Think about it this way: if you hadn't heard of it before, how would one rediscover the Lagrangian approach? So this is what we'll do, and to do this, we'll need some basic ideas concerning vectors. Now, vectors can be thought of in several ways. In basic terms, a vector is a column with numbers in it, such as this vector x, which has two entries called the components. Because two numbers describe any point in the plane, we might think of a vector as describing the position of a particular point. Vectors can also be thought of as arrows that point in a particular direction and have a certain length or magnitude. So I can identify this point x with an arrow that starts at the origin and finishes at that point. It moves across x1 units and moves up x2 units. This doesn't seem to be different at first, but notice that by thinking of vectors as arrows, I will say that this vector and this one are both the very same vector. So this is the interpretation we will stick with here. There is a much more general way of thinking about vectors simply as abstract objects for which vector operations, being addition and scalar multiplication, are well defined. Essentially, we only talk about vectors when we plan to use these operations. So what do they mean here? Vector addition is quite straightforward. If we take two vectors, x and x prime, then their sum is found by adding each of the components. Geometrically, we can think of starting at the origin, following the first vector to its tip, and from there following the second vector to its tip. So this longer vector, x double prime, is the sum of x and x prime. You can see that the order of addition doesn't matter here. The final result is the same, something that's known as the parallelogram law, and you can see why. Notice that x prime is the difference between x double prime and x. So thinking of vectors as arrows allows us to think of the vector between 2 points as the difference between those 2 points. Scalar multiplication, which means multiplying a vector by a single number, is exactly as you might expect. Just multiply each entry by that number. This results in vectors with different lengths. But if we're multiplying by positive numbers, they all point in the same direction. So the vector 0.5 times x points in the same direction as x, but is only half as long. And the vector 1.4 times x again points in the same direction, but is longer. Indeed, if two vectors point in the same direction, then they must be related by scalar multiplication, and we will say they are proportional to each other. Scalar multiplication by negative numbers, I'll let you figure out what that does. The next concept we'll need is the dot product, which we'll introduce just by showing how it's calculated. Given two vectors a and b, the dot product of a and b, which we'll write as a dot b, is found by taking the product of the first entries of a and b together, and then adding this to the product of the second entries of a and b. Notice that the dot product of two vectors is a single number, not a vector. Now, there is a way to understand the dot product geometrically, but here let's just point out one occasion where we've already seen this type of operation. Consider a vector p, which is a vector of prices. P1 is the price of good 1, P2 is the price of good 2. Also consider a vector x, which is a vector of quantities of these goods. Well, then the dot product of P and X tells you how much money you need to buy vector X given price vector P. We can express the budget line, which we have seen before, as all of the vectors X such that the dot product of P and X equals the consumer's income. From our previous work, we know that the slope of the budget line, which we called the marginal rate of transformation, is negative P1 over P2. But what does the price vector look like? Which direction does that arrow point? Consider 2 points, x and x prime, both on the budget line. Since both x and x prime are on the budget line, their dot products with the price vector are equal to each other, both being equal to income m. The vector that points from x to x prime is the difference vector. Notice that the dot product of the price vector and the difference vector is equal to 0. This actually tells us something about the price vector itself. It must point in a direction perpendicular to this difference vector, and so is perpendicular to the budget line. Whenever two vectors have a dot product of 0, they must be perpendicular to each other. To see this, consider this triangle. To show that this is a right-angled triangle, we can show that a squared plus b squared equals c squared, as this only holds for right-angled triangles. To find length a, the length of the price vector, notice that p moves p1 in the first dimension and p2 in the second, and so a squared equals p1 squared plus p2 squared. To find length b, notice that this vector increases x prime 1 minus x1 in the first dimension and decreases x prime 2 minus x2 in the second, so b squared is equal to this. To find the length of c, we use the same idea, noting the changes in the first and second dimension to find c squared. Now grab a pencil, pause the video, and show that this equals a squared plus b squared minus twice this dot product, which we know is equal to 0. And so this is indeed a right-angled triangle, which means the price vector is perpendicular. This is a right angle. And of course, this holds at any point on the budget line. Now let's consider indifference curves. If we take any point x on an indifference curve and consider the tangent at this point, then we know the slope of this red tangent line is the negative of the ratio of partial derivatives of the utility function evaluated at this point. Of course, this red tangent line has a constant slope, so if we pick another point x prime, then we know that this equation holds. If this isn't immediately clear, then take a moment to figure out an expression for this red line. You already know its slope, so introduce any notation for the constant term and then verify the above equation. Notice that this already looks like something involving dot products. To be precise, we can write this equation like this, where we're taking the dot product of each vector with this vector of partial derivatives. This vector of partial derivatives has a special name and notation. It is called the gradient vector of the utility function, and we use this upside-down triangle, or nabla, to denote the gradient vector. So let's use this notation here, and rearranging gives us a dot product equals 0 type of expression that we've seen before and we already know how to interpret. The gradient vector of the utility function at x is perpendicular to the indifference curve at x. For nonlinear indifference curves such as this, the gradient vector at each point will be different. At point x prime, it looks like this. At point x double prime, it looks like this. As an aside, if you read up more about gradient vectors, you will soon learn that they always point in the direction that the function increases fastest. To get the idea, if two indifference curves are very close together, then they are almost parallel. Think about the quickest way of getting from this point x to the next indifference curve. You will see that following any vector other than the gradient vector is going to take longer than following the gradient vector. This is often phrased as gradient vectors point in the direction of steepest ascent. So let's get back to the consumer's utility maximization problem. We know that the solution x star occurs where there is a tangency between the budget line and an indifference curve. The utility gradient vector at this point is perpendicular, and so is the price vector. Although the utility gradient vector and the price vector point in the same direction, this does not mean that they are the same vector. Their lengths may well be different. But as they point in the same direction, the price vector must be a scalar multiple of the utility gradient vector. They must be proportional to each other. That is, there exists a constant lambda star such that this equation holds. This lambda star is called the Lagrange multiplier, and the so-called method of Lagrange multipliers means solving this equation. This equation involves vectors, but we can read off two components. The partial derivative of utility with respect to good 1 equals lambda star times the price of good 1, and the partial derivative of utility with respect to good 2 equals the same lambda star times the price of good 2. Of course, with three variables, three unknowns here, x1, x2 and lambda star, and only two equations, we won't get far. So we need a third equation, but this is simply that the budget constraint holds with equality. The consumer spends all of their money. Now, when you first use calculus to find maxima or minima, you learn to find the value that makes a derivative equal to 0. So it might be slightly jarring for the solution to not involve partial derivatives being 0 and also to have this third condition tacked on afterwards. So perhaps it would be nice to restate this slightly in a way where the same conditions just pop out naturally. This is the essence of the Lagrangian. The idea is to take the constrained optimization problem, maximize utility subject to this budget constraint, which I've rearranged as income minus expenditure equals 0. We then combine the ingredients of the problem to form the Lagrangian, a function of the vector x and also this new variable lambda. And this function equals utility plus lambda times this constraint. Having done this, we can write the first order conditions in a very neat way. The gradient of the Lagrangian equals a vector of zeros. What does this give us? Looking at each component in turn gives three conditions, and we immediately see that these are precisely the conditions we already know. So nothing new as such, just a very neat repackaging of the same ideas from earlier. There is more to do, but if you followed the ideas here, then understanding the role of constraint qualifications, complementary slackness conditions, and so on should be a lot more approachable. Also, extending to many dimensions and many constraints, we could then write a vector of constraints and construct a Lagrangian with a vector of lambdas, and the first order condition is going to look pretty much the same. So that's nice. What's more, all these lambdas, which we only seem to need as a trick for solving the problem, actually contain useful information. So don't throw them away just yet, and perhaps we'll get to that another time when we consider envelope theorems. Thanks for watching, and take care.